let me start writing these basic properties for logarithmic function. We have that log in base a of x times y is log in base a of x plus log in base a of y. We have that log in base a of x over y is log in base a of the numerator minus log in base a of the denominator. We have that log in base a of x to some power is the exponent times log in base a of x, and finally log in base a of a number. We can do that using natural log as log in base e, natural log of x, over natural log of a, or we can use log in base 10 like this. Okay, we have these properties, and maybe the most important one is the one that defines log. We have that if we have this equation log in base a of x equal y, this is the same as having a to the y equal x. We can interchange the equations. If you have this equation, you can interchange it like this, and if you have this, you can write it like this. Let's see one first example. If we have a log in base 2 of x plus 3 equal 4, how to solve for x? Then we use this and we rewrite. And we have, this can be rewritten as 2 to the power of 4 equal x plus 3. Notice that the x is inside a log, but then when you use this rewriting, the x is out, and then now you can solve for x. Then here we have that 16, 2 to the 4 is 16, equal x plus 3, and therefore x is going to 16 minus 3, 13. Let's see another example. Log in base 3 of x plus 1 minus log in base 3 of x plus 2 equal 1. Then before using this equation, we're going to use this property to write it as a single log. Then we have log in base 3 of, this is the difference of two logs, then is a log of a quotient, x plus 1 over x plus 2 equal to 1. And now we rewrite, the base is 3, and we can write this as 3 to the 1 equal to x plus 1 over x plus 2. And we solve for x by multiplying by x plus 2 both expressions. Remember that if you have like a over b equals c over d, that means that ad is equal to b times c. Essentially, this is what we are using here. Then from this equation, we get that 3 times x plus 2 is equal to x plus 1. Then we expand, 3x plus 6 equal x plus 1. And then we collect the terms that has an x. Here we have 3x, and here we have x. We move the x to the left, and we get 2x equal 2 and 1 minus 6, which is negative 5. Therefore, x is negative 5 half. When we are using logs, it's important to replace back in the original equation. And the reason is that we know the log of a negative number doesn't make sense. In this case, this is the only possible solution, but if we replace back in the original equation, we notice that it's not going to work, because we will have log in base 3 of negative 5 half plus 1 minus log in base 3 of 5 half plus 2. But this number here is not defined, because this is log in base 3 of negative 3 half. And if we're working with real numbers, log in base 3 of a negative number doesn't make sense. That means that this x is not a solution. When we do this process, we get that this could be the only solution, but when we replace, we get that it is not a solution. Let's see another example. Let's have example 3, log in base 2 of 2x plus 7 minus log in base 2 of x plus 2 equal to 2. Then we do something similar to what we did last time. We write this as log in base 2 of 2x plus 7 over x plus 2 equal to 2. We use this property, and now we rewrite the equation, and we get 2x plus 7 over x plus 2 equal to 2 to the 2, which is 4. And then we multiply by x plus 2, we get 2x plus 7 equal to 4 times x plus 2. And then we have that 2x plus 7 equal 4x plus 8. And then when we move the x to the left, we get 4x minus 2x is 2x, and 7 minus 8 is negative 1, and that means that x is equal to negative 1/2. This is the only possible solution, but let's replace back in the original equation to see if that works. Then here we have log in base 2 of 2 times negative 1/2 plus 7 minus log in base 2 of negative 1/2 plus 2. And we see that this time is going to work because we are computing logs of positive numbers. 7 minus 1 is 6, log of 6, minus log in base 2 of 3/2. And then this is just using the property. This is log in base 2 of 6 over 3/2, and this is log in base 2 of 12/3, which is 4, and this is 2. As long as you have that the value of x makes sense in the function, in the sense that we are computing log of a positive number, then the number is going to work. Okay, then we have this example. Let's do another example in which we are going to use this property. Let's do something like log in base 2 of x plus 2 plus log in base 2 of x minus 7 equal to 3. Then in this case we apply this property and we get log in base 2 of x plus 2 times x minus 7 equal to 3. And now we use this property here and we get that x plus 2 times x minus 7 should be equal to 2 to the 3, which is 8. And we expand. This is x squared minus 7x plus 2x minus 14 equal to 8. And we notice that we are dealing with a quadratic equation. And when we have a quadratic equation, the way to solve it is to set it up equal to 0 and use the quadratic formula. Here we have x squared minus 5x minus 14 minus 8. It will be minus 22 equal to 0. And then we use the quadratic formula. In this case, negative b plus or minus the square root of b squared minus 4ac over 2a. These are the possible values for x. And in this case, b squared minus 4ac is going to be equal to, b is negative 5, negative 5 squared is 25, minus 4 times a is 1, c is negative 22, and this is 25 plus 88, and this is 8 and 5 is 13, 8 and 2 is 10, 113, and then the values for x are negative 5, negative b, which is plus 5, plus or minus a square root of 113 over 2, and then we get two possible numbers. Let me do those in the calculator. Okay, we have these two values, and let's see if they make sense when we replace them back here. When we replace the 7.815, we get that this is a positive number, and log in base 2 of a positive number makes sense. And when we replace the 7.815 here, it makes sense as well, right? And then this answer makes sense because 7.815 minus 7 is a positive number, and then this is going to make sense. But when we replace the negative 2.815 here, this part inside the parentheses is negative, and therefore this doesn't make sense. That means that in this case the only solution is 5 plus a square root of 113 over 2, which is approximately equal to 7.815. Let's suppose that a biologist recorded an amount of 500 bacteria, let's say after 10 minutes, and let's say that it recorded 20,000 bacteria after 40 minutes. That means 30 minutes later. And let's suppose that we are assuming that the bacteria follows an exponential growth model. That an exponential growth model is of this form, like a e to the k times t. This is the exponential growth model, and in this case, when k is bigger than 0, we call it exponential growth. And actually, when k is less than 0, it's not called exponential growth, but it's called exponential decay. Something interesting is that every exponential function can be written like that. For example, if you have y equal 3 times 2 to the x, then we have that 2 is equal to e to the natural log of 2, right? You can check that this is true, and therefore 2 to the x is e to the natural log of 2 to the power of x, and this is e to the x times natural log of 2. And then in this case, this function is just 3 times e to the natural log of 2 times x. That means that the k is natural log of 2. Then every exponential function can be written in this form. But we are assuming this. And now let's see this information, and essentially we want to find the a and the k. We have that the amount of bacteria, 500, is equal to a, that we don't know, times e to the k, that we don't know, times, let's suppose that t is in minutes, 10 minutes. And then we have this equation. On the other hand, we also have that 20,000 is equal to a, that we don't know, times e to the k, that we don't know, times 40, right? Because t is 40. How can we solve for a and k? Something that we can do is we can divide this equation by this equation. When we divide that, we get 20,000 over 500 is equal to a e to the 40 times k over a e to the k times 10. The a cancel out, here 2 zeros cancel out, 200 divided by 5 is 40, and then here we get e to the 30 times k. Remember that a to the n over a to the m is a to the n minus m. 40k minus 10k is just 30k. And now we apply natural log on both parts. Anytime we are looking for a variable, and that variable is an exponent, then we apply natural log, and then this exponent is going to go down. Then natural log of 40 is equal to natural log of e to the 30k, and therefore natural log of 40 is 30 times k times natural log of e, but natural log of e is 1, and therefore we get the natural log of 40 is equal to 30k, and therefore k is natural log of 40 over 30, and this number is 0.12296. Okay, we have the k. Now, how do we find the a? We can find the a by, erase this part, by using one of the two equations. That is that we have that 500 is equal to a times e to the 10 times k, but 10 times k is 1.2296, right? And now a is just 500 over e to the 1.2296, and this will give us the value for a. A is 146.2 approximately. Then we know a and we know k, right? We know that the amount of bacteria times e to the k, which is 0.12296 times t. With this information, we can answer questions like, what was the initial amount of bacteria? Then that is when t equals 0, and then when you replace t equals 0, e to the 0 is 1, and then the initial amount of bacteria was approximately 146. We can answer questions like, what is the amount of bacteria after 1 hour? Then after 1 hour, we write that down, amount of bacteria after 1 hour. 1 hour, we're working in minutes, is 60 minutes. Then we just replace, and we have 146 times 2 times e to the 0.12296 times 60, and this will give us 233,882. Also, we can answer questions like, how long does it take to double the population? We know that when t equals 0, we have approximately 146, and then we want to find the amount of time that it takes to reach 2 times 146.2. That means that we have to solve this equation. 2 times 146 times 2 equal to y, right? Y, which is 146.2 times e to the k times t. We can divide by this number. When we divide by that number, this cancel out, and we get that 2 is equal to e to the 0.12296 times t. If we apply natural log in both parts, then we get that natural log of 2 is the k, which is 1.2296 times t times natural log of e. Natural log of e is 1, and that gives us that the number that the t is natural log of 2 over 0.12296, and this is equal to 5.637. That means that approximately every 5.637 minutes, the amount of bacteria doubles. It doesn't matter at what stage you are at. After 5.6 0.37 minutes, the population or the amount of bacteria will double. This is one of the properties of the exponential function. The time that it takes to triple is always the same. It doesn't matter where you are at. Notice that here the formula for the time that it takes to double is equal to natural log of 2 over k. If we have an exponential model like this, then the amount that it takes to double is equal to this. Okay, this is it for this video.